I have 15 different best practices to cover and not a whole lot of time to cover them. So I'm going to kind of launch into it. These are best practices for how to design an image using a Docker file, then how to actually build the image, run the Docker file, and then deploying the image, and how to set up an application to be built to manage so that the cluster and other tools can manage the application more easily. The first best practice is that you should build your application image from a Red Hat Universal Base Image, a UBI. A UBI is something that comes from Red Hat, and in that image, they use Linux libraries that come from Red Hat Enterprise Linux. And those libraries are built and designed to be compatible with the Linux kernel that is running in OpenShift or that OpenShift runs on. So this way, you know that your image and the kernel are going to be compatible. Also, a UBI tends to contain, most UBIs contain a language runtime for popular, there's different ones for popular languages like Java, Node, and so on. So you choose one of those, and that way you've already got a language runtime built in. And so all you need to do is deploy your application into that language runtime. UBIs can run not only on OpenShift, but also can run in Kubernetes, and there's no license fee involved. So this is definitely the best way to build an image so that it'll run in both Kubernetes and OpenShift. And so that when you run it in OpenShift, Red Hat will provide support for it for the parts that they built, the parts in red. The way you do that is in your Docker file, you use a from command. And in that, you specify one of the UBIs. Make sure to get it from Red Hat's registry, and you specify which UBI it is that you want to use. In this case, we're using the OpenJDK one, so this will be used for running Java applications. The second best practice is to run your container as a non-root user ID. So when you use a Docker file to build a container, by default, the Docker file runs as root and the container will run as root. And that generally is not a good practice. So Kubernetes will run a container as root if that's the way it's been built, and that's okay, but it's a security problem because if that process running as root manages to break out of the container, well, now it's in the Linux kernel running as root and it can do anything it wants on the machine, and that's not good. So a best practice for Kubernetes is that you should build and run the image as a non-root user. That way, Kubernetes is a little bit more secure than it would be otherwise. To help avoid this problem, OpenShift doesn't care what user that you set in the Docker file to run the container as. OpenShift is going to use its own arbitrarily appointed non-root user to run your container. It uses a different user to run every container, and if you run the same container twice, if you stop it and start it again, it'll probably run with a different user than before. So you never really know what user it's running as, which is good. This is a security feature. And so what that means is that you need to design your container to run as non-root. That sometimes your container, your process does stuff that it manages to do successfully because it has root access, that when you run it as non-root, it no longer has that access, and sometimes things fail and you get permissions errors. So here's how you design your image and your Docker file to run as non-root. Is in your Docker file, you use the user command and you set it to any non-root user ID. By default, oftentimes we tend to use user 1001. Now, also, if you're building on top of a UBI, most of the UBIs have a user built in called default. So if you just say user default, then you'll get whatever user that uses, and that's good. So what you're doing is you're setting up a image, a container that will run as a non-root user and run properly, so that way when OpenShift runs it that way, it'll still run correctly in OpenShift. Next, what we want to do is to embed information inside the image about the image. So information on who built it and what it's for and that sort of thing. The reason for that is that as you take the image and copy it from one registry to another, you can lose track of where this image ever came from. And so we want to embed the information inside the image so that by looking at the image, you can tell who built it and what version it is and get a description of what's in there, things like that. So on the left side, we show in the Docker file, you use the label command and you set particular labels like name, version, description, that sort of thing. And then when you've built an image that way, then from the command line, you can run the inspect command and it shows you all kinds of stuff about the contents of the image, including the labels. So you can see who built it and what version it is and that sort of thing. This doesn't change the way your application runs, but it does change the information that's included inside the image. And so it's a good practice in general. It's a good idea and it's also required for Red Hat certification. The next thing we want to do is also embed license information inside the image. Again, when the image is passed around from one place to another, the license files outside the image can get lost. And so instead, what we want to do is build them into the image so that they're always there. And so this is whatever licenses are needed for the software that's running in the image. So including any sort of open source projects that you include, anything like that. So what you do is on the file system in the same directory as your Docker file, create a licenses directory, and then inside that directory, put any license files that you need. And then in your Docker file, you run this copy command, which copies the licenses file into the directory in the image that Red Hat specifies. And that way, all those files will get included in the image. This is a good practice in general, and it's required for Red Hat certification. The next thing we want to do is when we're building the image, we want to make sure that the image contains the latest set of security patches that are available. Now, if you're using a UBI and a pretty recent one, then it already contains the latest security patches. But there's always the possibility that another new security patch has been released since that UBI was built. And in any case, it's just a good thing to double check and make sure that your image has all the latest security patches. So the way you do that is in your Docker file, you use the package manager to go get the latest set of security patches and install those in your image. Whichever ones are already installed won't be installed again. So usually this doesn't actually change anything in your image. But if there are any security patches available, then it'll make sure to install those so that your image has all the latest security patches that are available. This is a good practice in general, and it's required for Red Hat certification. The next thing is any files in the local file system that the process wants to be able to access, you need to be sure to set the ownership and the permission so the process will be able to do that. Again, most containers manage to get away with this because the process is running as root, and so they're able to access things no matter what. But that's not a good security practice. So instead, we're going to run it as a non-root user. And so then how are we going to be able to access those files? So here we're talking about files that are in something called some directory. So whatever directory you want to use. What you want to do is in the Docker file is run this command, which is going to set the user to whatever user you're using to run the image, and then sets the group to 0. And the reason that and then sets the permission so that those users and groups can access the files. And the reason that we're doing that is because that way, if you run this image as a container in Kubernetes, it'll be running as the user that you specified, and that user owns the files, and so the process will be able to access the files. If you run that same image in OpenShift, then the arbitrarily assigned user ID that OpenShift uses, all of those are a member of the root group. And because the root group, you assigned ownership to all of these files and access, then that means that whatever user is being used to run the container in OpenShift, that process will be able to access these files because these files are owned by the root group. This is not required by OpenShift. You don't need it for Red Hat certification, but this is a common problem that people run into in OpenShift because, again, their containers are designed to run as root. OpenShift is the first time they run it as non-root and they find that it doesn't have file access. This is how you handle those file access errors to enable the process to be able to access the files. The next practice is to build an image in 2 stages. And the reason that we're doing that is because oftentimes to take your source code and build it into deployment artifacts, you need builder tools. And those builder tools, you need them at build time, but you don't need them at runtime. And so we don't want to include them in the image that we're going to deploy into OpenShift or Kubernetes for that matter, because all it does is make the image bigger and that causes bloat and that lowers container density that you can get on a node. Also, generally, it's not a good practice to include your builder tools into a production image because, in theory, somebody could hack into your image and use the builder tools to compile and deploy their own source code, which you certainly don't want to have happen. So, as a practice, don't include the builder tools in your image that you deploy into production. Well, so how do you avoid that? What you do is you use a two-phase build or a two-stage build. And so the first stage is called the builder image, and the second stage is usually called the deployment image. The first image is the one that has the builder tools installed, and that's where you build your source code and build your artifacts. And then the second image is the one that you're going to deploy. And that one needs to be built on a good base image. And then that one is going to copy the deployment artifacts from the builder image into the deployment image. And then that's what will end up getting deployed. The builder image will end up getting thrown away at the end of the build. This is a very good practice that's good for both Kubernetes and OpenShift. It's not required for Red Hat certification. It's just a good idea. Next practice is what not to do. Maintain the original base image layers. What that means is that the base image contains a bunch of layers, do not, which contain Linux libraries and usually a language runtime. Do not override those layers in your own layers. You can add layers to contain your own application and things like that, and that's fine. But don't add layers that override stuff in the base image because then you're defeating the purpose of the base image. So it's a good practice not to do this, and it's also required for Red Hat certification. Another thing not to do is to build an image with more than 40 layers. Your image should have fewer than 40 layers. This is just a limit to make your image manageable and run more efficiently. A typical image has 5, 10, maybe 15 layers in it. That should be plenty. If you get up to 20 layers, you're probably doing something wrong anyway. 40, you've definitely done something wrong. So build an image that only has 5, 10, 15 layers in it, and you'll be fine. And you'll be under this limit because, and the reason that's important is because if an image has a few layers in it, then that actually makes it more efficient. But if it has a whole bunch of layers in it, that actually makes it less efficient. So we're looking for that sweet spot where the image can be as efficient as as practical. And the way you can check that is on the command line, you run the history command and it shows you the layers in your image. And then you just need to count how many layers that it has and make sure that it's a reasonable number. If it's not a reasonable number, you've got a problem with how you built your image. This is one, a good idea in general, and two, it's a requirement for a Red Hat certification. All right. So that's kind of how we design the Docker file to build our image. So now I've got a couple of practices on how we're gonna do the build and run the Docker file. So these things, so the first one of those is that you should use build tools that are OCI compliant. OCI is the Open Container Initiative, which is a specification standards group that has written 3 specifications for how an image is supposed to work, how registries work, and how the runtime in a container engine works. And the beauty of building images that are OCI compliant is that then they will be able to run in any container engine whose runtime is OCI compliant. So this way you're not locked into a particular container engine. You can use pretty much any one you want. This way you can avoid vendor lock-in. That you're not stuck with one vendor. You can use a container engine from another vendor if you want. So the way to do that is to use OCI compliant build tools. And Red Hat has produced a set of those called Builda, Scopio, and Podman. And so what we recommend is that to run your Docker file and build your image, that you use Builda to do that because it builds OCI compliant images. You can also use Docker to build your image, and it also builds OCI compliant images, but it's a little bit trickier and you need to be a little bit more careful. If you use Builda, there's no tricks to it. It's easy. And furthermore, the images that it builds are optimized a little bit to run better in Kubernetes and OpenShift. So it produces something better. So the way you do that is on the file system, then you run the command is builda, and you specify the Docker file as your parameter. This is not required for Red Hat certification. It's just a good idea. Then the next best practice is uniquely tag each image. And what that means is don't just stick the image in the registry with no tag. It'll get a tag called default, but that's not good. That's useful for other things. But what you want to do is not only put the image in the registry, but you want to give it a tag that is unique from all the other tags for that image. Generally, what the tag should specify is the version of the software that's in the image and which particular build of the image this is, so that if you build the image over and over again, you increment that number and you know which build you've got. So here we show an example where we've built an image and then we tag it with 1.0-1 and 1.0. Those are aliases for the same image. And what that means is that this is the first release of the software, and it's also the first build of the image. Not only is this a good, that way when you push these images into another registry, then those tags go with it. Not only is this a good idea, but it's also required for Red Hat certification. Next, what I want to talk about is 4 practices for that we call to make an application what we call build to manage, which is an application that is easier to use in production. And so the first of those is that you should use container status probes. There's the 2 main ones that we tend to use in Kubernetes are called the liveness probe and the readiness probe. And liveness is whether or not your container is running. Readiness is whether or not the application in the container is running. And when you set those, then the cluster can use that to figure out whether a container is running properly, whether or not an application is running properly, and therefore it can optimize your application and make it run more reliably and more optimally within the cluster. You can make these things fairly complicated, although they run a lot, so you want to make them fairly quick. But a really easy default is just to say the root path on the main port that you're using, and that's good enough for it to be able to tell, is it alive, is it ready? And that makes your app much more manageable. It lets the cluster manage it much better. The next practice is specify a pod's resource requirements. What it's doing here is the pod is saying the size of the container, what resources it needs to run. So usually that's CPU and memory, and it actually specifies the resources in the pod specification, and it specifies 2 aspects: the requests and limits. Request is the minimum size that the container is going to start with, and the limits is the maximum size that the container can grow to in vertical scaling. It's perfectly all right to set these numbers to the same amount. And what that means then is that the container will not be able to vertically scale. And so you get your scaling using horizontal scalability. The next one is health endpoint. And what we want to do there is to create a URL for a RESTful service that you can run on the application that tells that answers how healthy the application is. This is something that a monitoring tool can use to figure out, is the application running? Is it healthy? Are there any problems occurring that the monitoring needs to do something about, or at least tell somebody about? By default, the easiest way to implement a health endpoint is as a Boolean that basically says, are you running? Yes or no. So here we're saying that the health is up, so that means yes. What the monitoring tool does is, as long as the application is saying yes, well, then that's a good sign. If the application ever says that it's down, or if the monitoring tool doesn't get a response at all, then it thinks the application isn't running and it's going to try to take corrective action. And the last best practice is logging events. And so this is when your application has trouble in production. Then you look at the logs and try to figure out what it was doing and try to get an idea of what went wrong and therefore how to fix it. And so you can the way you do this is you're going to use a logging library. There's lots of them available for lots of different languages, so you can use any one you want. The main thing is that the library needs to log the system out. That's important because that way log aggregators can connect to system out on all the different containers and gather all the logs and aggregate them all together into one set that's a lot easier to use. And so in there, you use your logging library to log interesting things that the application is using. These are things that you would want to know when you're trying to debug the application, trying to figure out what went wrong.